So the next speaker is Or Sattath from Ben-Gurion University, and he will talk about the insecurity of quantum Bitcoin.
Thank you. This is the archive number for those interested. So I'll start with the summary. Some of the terms here will be made clear during the talk. So the Bitcoin network becomes less secure once Bitcoin miners use a quantum computer. The reasoning is as follows. Once quantum Bitcoin mining will start, the stale rate, which will be, again, explained in the talk, will increase. And there are known bad implications for this. For example, it makes double spending easier. Selfish mining becomes profitable with a smaller hash rate. It takes longer for transactions to confirm and various other things. And we have a proposed solution for that, which I'll also present. So I'll start with explaining how Bitcoin works. Bitcoin in general is a peer-to-peer digital cash system. And we'll explain how it works in a series of attempts. The last attempt will be fairly similar to how Bitcoin really works. So in the first attempt, assume you have an append-only globally available public bulletin board, meaning everyone can access this bulletin board and read its content, and people can only add messages to this bulletin board and never delete things from it. So how could you use such a bulletin board? So here's the first attempt. We first have some distribution phase where Alice, Bob, and Charlie gets 10 coins each, and then if Alice wants to send them 2 coins to David, she simply appends this message to the bulletin board. And if Charlie wants to send, he does a similar thing. But then let's see what happens if Alice appends the message, Alice sent 20 coins to Francis. Well, Alice does not have 20 coins, right? So we all agree that if that this is an invalid message and it is ignored, right? So if someone doesn't have the amount to pay, it is simply ignored. But obviously, there's a problem here. What happens if David appends the message, Bob sends 10 coins to David and steal all of Bob's coins? Right? This is clearly a problem. So for that, we'll use digital signatures. I'll recap what digital signatures are. So we have a signer who generates a secret key and a public key pair, keeps the secret key put to himself, and publishes this public key. Using the secret key, the signer can sign messages, which can be verified by everyone else using the public key. And these, no one can forge these signatures without the secret key. So how do we change the protocol? So now, instead, we also add in the distribution phase the public keys of the users. This is called the Bitcoin address in Bitcoin terminology. And now when Alice wants to send some coins to David, she signs this message. Now everybody checks that this signature is valid and therefore it is accepted. And let's see what happens if David tries to append the message, Bob sends 10 coins to David. But now, of course, he won't be able to forge Bob's signature, right? And therefore, everyone will notice that this message has an invalid signature and, again, ignore it. Good. So now we're facing the problem of, well, actually 2 problems. How do we construct this append-only bulletin board, and the second is how do we distribute the money in a peer-to-peer network, right? So for the first problem, we'll use something called proof of work. I'll explain how it works. So a cryptographic hash function, such as SHA-256, is modeled like a random function from arbitrary long bit strings to 256 bit strings. Now, how is it used? So transactions are flooded to this peer-to-peer network, but if they are there, this doesn't mean that they are valid. It just, everybody can hear about them. And in order to make these transactions valid, miners need to include them in a block. What is a block? So a block contains some things you can see here. This is the block. It contains the previous block hash, the time, something which is called a nonce. This is just some arbitrary number, and the transactions. And a block is valid if the hash is smaller than some value t. This is called the target or the difficulty. Now, this threshold T is adjusted so that a block is found every 10 minutes on average. I won't get into the details. You can look here how it's performed. And the time is only used for that, for adjusting this, this parameter T. This mechanism is called proof of work, and classically, it is progress-free, meaning the time you spend so far on finding a block does not affect your chances in finding the next block in the next few minutes. Okay, so a miner who finds this valid block, this requires work, and in return, this miner gets some bitcoins. It started in 50 bitcoins, and it is slashed every 4 years. And for miners to succeed, they just keep trying to find this nonce X, right? They just try and try and try X and hope to be lucky. This is very similar to how a lottery works. They just keep trying until they're lucky and win this lottery. Okay, so let's see an example how it works. So the first block is kind of special. It doesn't have a previous block, right? This is hard-coded in the protocol. This is called the Genesis block. And this was created by Satoshi Nakamoto. And as you can see, if you hash this block, the hash is 214, and the current target is 400, so this is a valid block. So now we have these 3 miners. They just keep mining and mining and mining. Oh, and miner 2 was the lucky miner. The hash of this block is 312, so it's a valid block, and it contains the miner's address, so he can receive these bitcoins in returns. This nonce X, which was just we just keep trying, and some transactions. Satoshi sent one transaction to some user. So now we keep going, and now there's going to be something that happens very rarely, but nevertheless I'm going to present here. What happened here is that 2 miners managed to find a block roughly at the same time without hearing about the other's block. So this is, in Bitcoin terminology, this is called a fork, and this happens roughly once a day. You can actually see it, of course, and what happens here is that we're in limbo, right? Look, here there's a transaction that user 1 sent some coins to user 2, and here there isn't such a transaction. So did it happen? Didn't it happen? We're in limbo, right? So we need to somehow break this symmetry. So currently, the way Bitcoin works is the longest chain rule. Like usually, reality is represented by the longest chain, but here we have a tie, right? So in case of tie, honest miners mine on top of the tip which they have heard first, right? This could be subjective, so they might not agree on this. And this is this symmetry breaking mechanism. How does it work? So here, let's see what happens. Miner 3 managed to tell miner 2 about his own block, about this bottom block, 233, before miner 1. So now miner 2, he's honest, he's mining on top of this block. And now let's see what happens. They all trying to mine. And now miner 2 was lucky. He found the block. Again, he's mining on top of this block. And now we have a clear winner, right? This is the longest chain. There's no tie anymore. And everybody, will, including miner 1, will mine on top of this longest chain. So this is the way to break this symmetry. Good. So you might ask, miners invest so much money, energy on this process. Why is it important? So in some sense, the Bitcoin miners provide a service for the Bitcoin networks. They provide security. The more hashing power working on this process, the harder it is to apply some attack called a 51% attack, also a double spending attack. So let's see how this attack works. So here we have miner 3. As you can see, he's slightly larger than the others. He has the majority of the voting power. And the way it works is as follows. First, he publishes a transaction that he's willing to pay for store 1. Sorry. Now, they have heard of it. They will, these small miners will mine and will find the block. And now here we have this block, which contains a transaction which says miner 3 paid to the first store. So now, obviously, the store will give him some ice cream, right, in return. But let's see what goes next. Now miner 3 joins mining, but in a malicious way. He mines on top of this block, and since he has the majority of the power, he's eventually will win this race, and let's see how. So now he added a transaction that miner 3 pays to store 2, right? He's now paying to a different store. So now we are in limbo, we have a tie, but miner 3 will continue doing so. And since he has, again, the majority of the power, it's like he has more votes in some sense, he will eventually win. And now let's see what happens. Now this is the longest chain. So this block is invalid now. And now from store 2 perspective, there is a user who paid, and therefore he deserves his ice cream. So miner 3 got his 2 ice cream, and this is why it's called a double spending attack, right? Good. So the crucial point here is that the more money invested in mining, the cost for this attack increases, and that's why it's so important to have this process cost so much. So it won't be easy to do. There's no other solution for this attack. So what happens in the quantum case? Some things are very well, already well known. The current digital signature scheme is broken. You can break it using a variant of Shor's algorithm. And the proposed solution is simply to use a post-quantum signature scheme. And that was already known. Another thing which was known is that you can use Grover's algorithm to solve this proof of work problem, or proof of work puzzle. And the immediate consequence of that is that the difficulty will increase. It will be harder to, this number t will decrease, but that doesn't seem like any problem. But again, this was already known. But now we'll have a crucial observation, and here is that's the main point of this talk, like this slide and the next one. So Grover's algorithm achieves a quadratic speedup. We all know about that. But it also achieves this speedup when it is stopped prematurely. You don't have to choose at which point to stop in advance. You can run it, if you feel like it, you can stop now or at any point you want. And the probability of success is t squared divided by n if you applied for t iterations. And this is crucial, the fact that you can stop prematurely. And let's see why. So suppose now someone else, your fellow miner, found the block, or competitor, actually. You could use one of 2 strategies. The first strategy is just simply to throw away your computation that you did so far and start mining on top of this new block. But this is silly, right? The right thing to do is to measure immediately and hope to win. In what sense? What does win means? It means both being successful in finding this nonce, so getting a valid block, and to propagate it faster to your peers, right? If you manage to pass it faster than your competitor, they will also mine on top of your block, and then you will receive your bitcoins. So it is obvious that strategy 2 is better than strategy 1. You're simply throwing a valuable resource in strategy 1. And therefore, everybody will use strategy 2. Now let's see what happens if everybody uses strategy 2. Once one miner finds a block, all other will immediately measure their state. So there is a strong correlation between the times in which the state is measured, and therefore there's the time in which blocks are created is highly correlated, and therefore there will be these forks. This is very different from what happens classically, where they just independently try. And one way to see it is that classically, if you take the propagation time, the time for these messages to travel to go to 0, then the stale rate goes to 0. But here, forks happen for a completely different reason, and this doesn't matter at all. It's not a network effect anymore. So here's some simple calculation that you can see that if you take symmetric miners and see what is the stale rate when they mine for 10 minutes, if they say mine if they invest in mining for 4 minutes, then the forks will happen roughly. There will be 20% of forks. As I've said, now it's roughly 0.1%. So it will be a dramatic increase. So we have a countermeasure for that. So the main idea is to prohibit this adaptive strategy we described before. The intuition is that the miners must choose in advance how many iterations they're going to apply. And how can we do that? So we'll change the tie-breaking rule. If you remember, the current rule is that if in case of ties, follow the tip that you received first. And the new rule is slightly more complicated. Suppose that there are now two competing blocks that you received at time t1 and t2. Then let t be the minimum between all of them, like the time that you received first. And let S1 and S2 the timestamps of these blocks. Now, honest miners will follow the block which minimizes S1 minus t in absolute value or S2 minus t in absolute value. And let's see why it makes sense. So suppose you're an honest miner, you planned to mine for 2 minutes. So the timestamp in your block would be 2. And like you will propagate your block to your neighbors, they will probably hear about it in a second or so. So this difference will be roughly 1 second. Now suppose you're this adaptive miner who planned to mine for 3 minutes. The point is that this timestamp is something that you cannot change. You have to, it's inside the block and it is hashed, and therefore you cannot change it. And therefore the difference here would be roughly 1 minute. And therefore the honest miners will mine on top of the honest block. So some discussion and open questions. It seems kind of hard to analyze the equilibrium of with the solution and without the solution of what will actually happen. There are some initial unpublished results by Troy Lee, Maharashi Ray, and Miklos Stanta, which I won't comment about. There are some questions regarding the security of the proposed solution. For example, currently the time is, the clocks do not really need to be synchronized for Bitcoin to work. And now we make extensive use of the time. This might lead to new attack vectors such as timing attacks on time servers, or I don't know, perhaps other things which I'm not aware of. Another question is regarding pooled mining. I'll explain what is pooled mining. So investors usually want to maximize their expected revenue and minimize the risk, the variance of their invest. And Bitcoin is like a lottery, right? It has a huge variance. So in pool mining, lots of people join together and share the revenue, and therefore they are getting roughly the expected value and have basically no variance. Now, what could happen in this setting is that pooled mining will be less efficient for some technical reasons, and therefore it will give advantage to bigger players, which again determine in Bitcoin, it's especially important to be a decentralized system and not to give advantage to bigger players because of this 51% attack. So that diminishes some of the Bitcoin's properties if this happens. There are other concerns, like there are lots of complicated attacks such as selfish mining, infiltration attack, pool hopping, and all of these things need to be addressed. How does it, whether the situation changes in the quantum setting or not. Again, even with this proposed fix, the Bitcoin will not be progress-free. And what are the implications of it? Is it a bad thing? I don't really know. And the last question is the high stale rate is known as a problem in the classical setting, but actually in the quantum setting, it stems for completely different reasons, and it's not so clear whether it is so problematic as it is in the classical setting. So that's it. Thank you so much.
Thank you all. Questions?
Hey, so you said that miners, when they behave rationally, they will lead to 20% forks, and you say that's a problem because of the double spending. But in reality, we wouldn't accept money anyway if it's only in one block, because whether it happens 20% of the time or once a day that there's a fork, we wouldn't want to risk that as a vendor. So vendors actually wait for a certain length of chain to confirm a block. So what I'm wondering, have you checked that the length of the block you would need actually increases? Because the forks happen, but they will be probably also quickly resolved because the longest chain rule still holds. So it's not obvious from what you said that this is really something that changes how long you need to wait to confirm something. So perhaps we can just keep using the existing Bitcoin, and the problem does not really lead to double spending.
Yeah. So let me try to address your question. Suppose it just happens classically. If I understand your question, is what's so bad with waiting for like, I'll just wait more. That's basically what you're saying, right?
No, I say it's not even obvious that I have to wait more. Perhaps two forks happen one forks happen all the time, but 6 forks don't happen more often than they do now. Because 6 forks never basically happen. So we have this, we wait for more, we wait for 6 blocks, not because 5 are likely to happen for rational behavior, but I think we do that because to reach an attacker who intentionally mines wrongly might reach 5 but not 6 or something. So one would have to analyze this whole thing, like everyone is rational and we have someone who tries to actually fork along a wrong chain or something.
Okay, I'll try to answer your question. Perhaps we should take it offline to make this discussion, to finish this discussion. But generally speaking, as you just said, the number of usually, especially exchanges, do not accept money after 1 Bitcoin. They wait for some number of confirmation, perhaps 6. The reason is that they are so afraid of this rare event that there will be the transaction would be reversed, and this is directly related to the rare event of these forks. This could happen for natural reasons, and it won't happen naturally after 6 confirmations, but if the stale rate would reach these values, it could certainly do happen, and therefore they'll have to wait for more confirmations. So that's one reason. Another is that if the stale rate, at least classically, if the stale rate is high, instead of having an attacker to perform a double spending attack needs 50%, now to double spend he perhaps needs 30% or 40%. So the percent needed to perform a double spending attack decreases. So that's why it's not only an efficiency but also a security concern.
Okay, let's discuss it offline.
Okay, we should move to the next talk, but before, let's thank Or again.